Hello and welcome to our final Zoom session before midterms. I'm gathered for 110. Today is March 5th, and I understand from email correspondence, I think your midterm opens tomorrow. So what we're going to do today is have a review. It's March 5th, 2019. We've done units 1, 2, and 3. We completed our last unit, number 3, on complex sounds. We took 2 weeks for that. We covered the decibel prior to that, 2 weeks. And I believe we spent 3 weeks covering frequency, wavelength, and speed of sound. So today what we're going to do is a review. Simply a review of units 1, 2, and 3. So without any further ado, let's do a review. All righty. We'll see what I can see. I will share screen here, and we'll pull up unit number 1. So let's pull this guy right here. Frequency, wavelength, speed of sound. And we'll highlight the areas. The purpose here is to highlight the areas that you should concentrate on for any type of midterm exam. And that would be the general idea. So we're just holding a good old review here. And we're in unit number 1. So if anybody wants to, I'll just kind of wait around while you pull up, and if you can pull these notes up for yourself. Unit 1, day 1, review. That's exactly what we're doing today. Okay? So in unit 1, basically, you should know that molecules moving around in the air without any sound, just random movement of molecules, is called Brownian motion. Then sound waves. Put a star by this one here. They're simply a series of squeezed and separated molecules. So when we go to the PowerPoint on unit number 1, and we see this particular slide here, these are condensations and rarefactions of molecules made by striking a tuning fork. These are sound waves, but we draw them as up and down. So here you're looking at, again, condensation and rarefaction of molecules. This picture is kind of hard to see. It doesn't look as good. This one here, it looks neater, okay? At any rate, this is an important concept. The squeezing and separating of molecules we draw as up and down motions of a wave simply because it's easier. Okay, so the up represents condensation, the down represents where the molecules are separated. So these bands here refer to these here. We move on down. Here's a speaker producing sound, 2 speakers. You can see a rarefaction, a condensation, a rarefaction, a condensation of molecules drawn as this sound wave here. There's 2 condensations, 2 ups, and 2 rarefactions, 2 downs. Okay? The bottom speaker, it's producing condensations and rarefactions as well, but there's more of them. They're smaller, they're tighter. And so this is producing a higher frequency. There's 4 bumps going up, 4 condensations. So you can think about the sound wave as time on the horizontal and amplitude on the vertical. And a sound wave has 360 degrees, just like a circle, starting at 0 to 90 to 180 to 270 to 360. All right. Here again, sound waves, 360 degrees. This is 1 wavelength, 1 condensation, 1 rarefaction. This is 1 rarefaction, 1 condensation. It hasn't changed. The only thing that's changed is the phase, this one or this one. Okay, they're the same frequency, the same, if this is 1 second, the time, and this was 1 second, the time, they're the same. It's just different phase. Here's another one. If this time hasn't changed at all, there's 1 wavelength here too, because there's 1 condensation, kind of split in half, and 1 rarefaction. So you're looking at the 3 dimensions of sound: frequency, intensity, and time. Frequency is on the top. These are the same in amplitude, just different in frequency, different in numbers of waves per second, known as hertz. And the bottom one, this is the same frequency, they're just different in amplitude. And the middle one, they're the same amplitude and same frequency, they're just slightly out of phase. Keep it simple. Here too. 3 different dimensions of sound are shown: frequency, intensity, and time. The top 2 waves are equal in frequency, but they're different in amplitude. The middle 2 waves are equal in amplitude, but they're different in frequency. And the bottom 2 waves are equal in amplitude and frequency, but they are in opposite phase. So, sound waves, period versus wavelength. Okay? When you're looking at a sound wave, you can talk about 2 different things. You can talk about the horizontal being time, or you can talk about the horizontal being the length of the wave. Okay? And this gets us into our weird little formulas that we need to know for this course. Period. The time, T-I-M-E, the time it takes to produce one cycle. So if we alternate what we're doing here and look at our notes and move down and scroll down, okay? Frequency and period. Right there. There's that section to digest right here. Okay? So you're looking at frequency, the number of times something happens per some unit of time. For sound, frequency refers to the number of cycles, the number of compression and rarefactions per second. Hertz is the moniker we give to it. So a sound with a frequency of 100 cycles per second is 100 hertz. And the period is the time it takes to complete one cycle. So if a sound is 1 hertz, then its period is 1 second. It took 1 second to produce 1 compression and 1 rarefaction. If a sound is 100 hertz, then its period is 1/100th of a second, because you had 100 bumps, 100 compressions, and 100 rarefactions per second. So period and frequency are inversely related. The higher the frequency, the shorter the period. Right here. F is 1 over P. P is 1 over F. All right, put a star by that. That's the first of 3 formulas to memorize in this course. Humans can hear from as low as 20 cycles per second, or 20 hertz, up to 20,000 hertz. And our very best hearing is for sounds between 1,000 and 4,000 hertz. And we've learned in 120 as to why that's the case. It's because of the outer ear canal resonance and because of the middle ear occipital resonance. Those 2 resonances, the outer and middle ear, make our best and most sensitive hearing at the high frequencies between 1,000 and 4,000 hertz. And that's the sweet spot of our hearing. And it's very important because that's where the high frequency consonants are that we mentioned in Unit 3, especially the unvoiced consonants like the letters S, F, TH, CH, SH, K, all those high-pitched sounds. So we're just tying it all together in a little loop here, so we've got it. Hearing tests are called audiograms, and they show hearing sensitivity from 125 up to 8,000. So we don't test all these frequencies in here. We just test 7 different octave frequencies. Many people don't even test at 125. They start at 250, 500, 1,000, 2,000, 4,000, and 8,000. Remember, when you go up 1 octave, you double the frequency. Here's the next set of formulas to memorize. Okay, now we're talking about wavelength. So in this particular picture, okay, where is it here? Here. In this particular picture, and I'll make it bigger. There. You can talk about time in the sound wave, or you can talk about the actual physical length of the wave. So we've dealt with the top one. Let's talk about the length of the wave. How long is it? How many inches long is the sound wave? How many feet long is the sound wave? You could look at it like that. Okay, here's period, amplitude and period and time. Okay, again, period, how many cycles took place in 1 second. And here's out of your textbook. But now you're looking at wavelength. Okay, same thing, only here you're looking at the distance, the actual length of the wave, and again, the vertical is the amplitude. Okay, so let's go and look at our notes and carefully have that puppy down here. Here we go. Just like period, wavelength is inversely related to frequency. As the frequency goes up, the wavelength gets shorter. Recall, period is also inversely related. So wavelength, however, involves the speed of sound. So wavelengths in water, wavelengths in air, wavelengths in steel, okay, they're all going to be kind of different, but we live in air. So let's look at air. Okay, wavelength involves the speed of sound in whatever medium you're talking about, and we care about air, over top of or divided by frequency. Just like you can say 5 is equal to 10 divided by 2. Okay? You can flip the formula around if you're trying to find, if you know what the wavelength is and you want to find out what the frequency is, or if you know what the frequency is and you want to find out what the wavelength is, you're going to do this one. Okay? If you know what the wavelength is and you want to find out what the frequency is, you're going to do this one. 2 is equal to 10 divided by 5. And all you're doing is flipping numbers around. And if you wanted to find out what the speed of sound was, I guess you'd have the frequency times the wavelength. 10 is equal to 2 times 5. So we don't want to get lost in the numbers here. Just memorize these two formulas right here. That's what you need to know. And the kicker, the clue, the easy thing to memorize them, the trick to getting these formulas always right is memorize the fact that that speed of sound is always on the top. Wavelength equals speed of sound over the frequency. Frequency equals speed of sound over top of the wavelength. Okay? That's the trick. Once you know that, you're good to go. So let's look at 100 hertz. We want to find out what its wavelength is. Okay? You know what the frequency is, it's 100 hertz. So wavelength equals the speed of sound divided by the frequency. Speed of sound is 343 meters per second divided by 100, 3.43 meters. That's how long 100 hertz is. You want to do it in feet? 1,130 feet per second is the speed of sound. Divided by 100, 11.3 feet. Okay, there you go. Always remember, keep apples to apples and oranges to oranges. For 250 hertz, 340 meters per second divided by 250 is 1.37 meters, or 1,130 feet per second divided by 250 is 4.5 feet. Same thing. But look at 8,000. Look at how high that pitch is. 340 divided by 8,000 is 0.04 meters. Now, what is 0.04 meters? That's about 4 centimeters. 4 fingernails. That's the width of a fingernail is about 1 centimeter. There's about 2.5 of those in an inch. So 4.04 meters, or 1,130 feet divided by 8,000 is 0.14 feet, like short, about 1/10 of a foot. Okay? So an important concept to remember for hearing aids is that lows bend and highs bounce. That's another thing. Just put a star by that one. Okay? So don't worry about this stuff, but oh yeah, this one you need to know. Okay, right there. That one's good to know. Okay, what's the speed of sound in water? 4 times that of air. In metal, 14 times faster. Speed of sound, this is poorly worded here, okay? This right where I'm doing here. But speed of sound deals with the mass and the stiffness of the medium through which it travels. The more dense a medium is, the more mass, in other words, a medium has, the slower the sound goes through. The more stiffness the medium has, the faster the sound goes. And so you might say, yeah, but Metal especially is way more dense than air, so why does sound go faster through metal? The reason why is because steel is also way more stiff than air. And the stiffness of metal compared to air far outweighs the greater density of metal compared to air. That's why sound goes faster through metal. All right. Moving on down. Here's another one that's always asked on a midterm, and a lot of people get this wrong. The speed of sound has no relation to the frequency. In air, all frequencies travel the same speed. In water, all frequencies travel the same speed. And in metal, they all travel the same speed. Doppler effect and sonic boom will not be asked on your midterm. Okay? Those are just simply interesting things to know. Just interesting stuff regarding the speed of sound. The Doppler effect happens below the speed of sound, and a sonic boom occurs above the speed of sound. Okay? And just have that just out of interest. Sound fields. You should know that an echo compared to a reverberation, know the relationship of those. An echo is a long reverberation. Okay? The time delay between original and reflected sound. If it's greater than 1/10 of a second, it's an echo. If it's a reverberation, it's less than 1/10 of a second. Think of a gymnasium and you're bouncing a basketball. Okay? That's reverberation, not so much echo. Meanwhile, if you yell across the Grand Canyon, hello, 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 that's echo. Okay. Good. Standing wave anechoic room. This is kind of just FYI for information. Anechoic room is a soundproof room. It means it has no sound bouncing. No sound bounces at all, and no sound comes in and no sound goes out. Okay, it's soundproof. Very, very expensive. We test hearing in sound treated rooms. Okay, sound treated rooms, which means you can think of sound treated as like water resistant compared to waterproof. Is a watch water resistant or is it waterproof? A sound treated room is where we test hearing. It's mainly to block out lots of sound, but not all sound. Good. Now we move toward the end of Unit 1. Impedance. I would know this as well. This is important stuff, and it's covered here and in Unit 3. Okay? You're running into this one in Unit 1 and in Unit 3. So make sure you have this one down. Okay? Impedance is opposition to the passage of sound. In any medium, there's impedance. Otherwise, sound would travel forever. And it doesn't. It slows down. Okay? It eventually stops. That's impedance. Now, impedance is caused by two things, resistance and opposition. Resistance and opposition. All right? Resistance is like simple friction. So in any object or in any medium, the friction of sound, like if you rub your hand really fast across the top of a desk, your hand gets warm. Okay, that's friction. And that's resistance. And in any object, the resistance to the passage of sound is equal for all frequencies. Here, right there. Independent from frequency. Okay? Anything. The resistance in anything. In a trumpet or a clarinet or an air or an electrical wire, whatever. The resistance is going to be equal for any frequency. But opposition is different. Opposition is sometimes called reactance. And it depends on the mass and the stiffness of an object. So an object with a lot of mass likes the passage of low frequencies, but it opposes the passage of highs. That's why when you're sitting in your room downstairs and the people upstairs are playing music really loud, what do you hear come through your ceiling? The bass guitar and the drums, because your ceiling is dominated by mass. And low frequencies can get through mass, but mass opposes highs. And stiffness is the opposite. The stiffer an object is, the less it likes to pass lows. It doesn't like lows. It stops lows. and it really lets highs get through. So in any particular object, the opposition will be very different for different frequencies of sound, because different objects have different mass and different stiffness. Now we get to resonance, and that's all that is impedance flipped upside down. And that's what I say all the time. A frown is an upside down smile. A smile is an upside down frown. Okay? So when you do that, when you're looking at resonance, it's just the flip side of impedance. Okay? What isn't impeded resonates with an object, gets through. So rubbing your hand on the rim of a wine glass until it goes, whoa, okay, you've hit the frequency that object likes, that it's passing through the most, and it's opposing other frequencies. You've hit its resonance. So as mass increases, resonant frequency goes down. As stiffness increases, resonant frequency goes up. Okay? And the last thing you need to know is the quarter wave resonator. The quarter wave resonator. But before we do that, I'll stop sharing for just a second here, and I'll pull out my little bag of tuning forks here and just show you. Okay? Big tuning fork, little tuning fork. Okay? So if I'm hitting the big tuning fork, it's got more mass and less stiffness. Look at this. I can even bend. I can bend these things. Whoa. Okay? And if I don't know what you hear, you probably hear some. If you really could hear through the speaker properly, you'd hear a low-pitched sound. All right? I'm not sure where the speaker is on here, where the mic is on this laptop I've got. But anyway, little tuning fork, there's no way I can bend its tines. It's way too stiff. Okay? And it has less mass. So see if I can really ding this thing. Okay? Mass and stiffness. Mass and stiffness. It's all in our field. It hangs the moon in our field. It's big. Okay? It's a big concept. Okay, quarter wave resonators. Now these are also often mentioned in our field. You've got two of them. One's the outer ear canal, and the other one is your mouth. Okay, speech. In your outer ear canal, it's 1 inch long or 2.5 centimeters long. And that is going to be because the outer, and it's closed at one end and open at the other. So memorize this fact too. All quarter wave resonators tend to resonate with sound waves 4 times their length. So if your ear canal is 1 inch long, it's going to resonate with sound waves 4 inches long. If your ear canal is 2.5 centimeters long, it's going to resonate with sound waves that are 10 centimeters long. Okay? Either way, whether you do it in feet or in metric, doesn't matter. The principle is the same. So, frequency equals speed of sound over wavelength. Well, we know what the wavelength is, so let's figure out what the frequency is. So wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. Well, if the wavelength is centimeters, so you know the sound wave is going to vibrate with sound waves that are 10 centimeters, do the math. 343 is the speed of sound, divided by 0.1 meter, which is 10 centimeters, is 0.1 meters. Now, always remember this. The 343 is meters per second. I can't divide meters by centimeters, so I can't do 343 divided by 10. Can't do that, okay? I have to change the centimeters into meters. So 10 centimeters is 0.1 meter. So 343 divided by 0.1 is 3,400 hertz. Okay? And that's similar to the outer ear canal resonance. Your outer ear canal resonance is sort of between 1 and 4,000 hertz. And it's made of flesh and bone. So the resonance is spread out, and it won't just simply be at that frequency. It's going to be mushed out a bit, okay? Basically, your outer ear canal resonance hovers between 1,500 hertz out to 4,000 hertz. Okay, helium speech. Here's your other resonator, your vocal tract. The length from your throat to your lips is about 17 centimeters. The speed of sound in air is about 340. So your vocal tract is going to resonate best with sound waves 4 times 17, and that's 68. Frequency equals speed of sound over the wavelength. So 343 meters per second divided by 0.68 meters, not 68, 0.68. Because you got to, again, change centimeters into meters. And when you do that, you get the math. There it is. And why does helium speech, when you inhale helium out of a balloon, why does your voice get higher? Because helium is less dense than air. So sound goes faster through helium. So now you're doing 927 meters per second divided by 0.68. And you get a whopping number of 1,362. Now you know why helium speech makes your voice go higher. It's all about quarter wave resonators and wavelength and speed of sound and all that jazz. Okay, that's Unit 1. And we spent almost half an hour on it. You know why? Because it's furthest back. Okay, Unit 3 we were just looking at last week, so it's more in your memories. But let's now go to Unit 2. Let's look at the decibel from hell. So without any further ado, let's look at Unit 2. All right, intensity, decibels, power, and pressure. Now, when you're looking at this unit, there's some stuff you need to pay attention to and other stuff not to worry so much about. Okay? This one, pressure, is force over an. Don't worry about pascals and newtons and all that crap. The pressure unit we care about is dynes. Okay? That's the one we're going to use. Dynes is a unit of pressure, and pressure is always force over an area. And you'll recall from 120 in anatomy, that's why you have a middle ear, to help increase the pressure of airborne sound, because airborne sound has to hit the eardrum, and the eardrum is way bigger than the footplate of your stapes. So the force against your eardrum is now converged onto a smaller area. You've thus increased your pressure. Hey, what hurts more? Putting your palm against the side of your face or putting a needle against the side of your face? I think the palm hurts less. Okay? If I have an X amount of force against my palm, my hand against my face, if I put that kind of pressure against a needle, my face is going to bleed. You're going to puncture your skin. Pressure is force over an area. Okay? So, we care about sound pressure. And we care about sound pressure because the ear works like a pressure device. It receives sound. Your ear is like a microphone. It picks up sound. You can talk about sound power or you can talk about sound pressure. We prefer pressure. But power is a different way, and we don't use it, but some people do. And power is reflected in the capacity to do work. Okay? And it's measured in watts per centimeter squared. So pressure, dynes per centimeter squared, power, watts per centimeter squared. Forget about all of that stuff, move down. Here's what you need to know. Put a star by that. In terms of power, the softest you can hear is 10 to the minus 16. Yikes, tiny. The largest power you can tolerate, 10 to the minus 4. The difference between those is 10 to the 12. That's how math works. I'm no mathematical genius, but 10 to the minus 16 is not larger. This should be reading smaller. 10 to the minus 16 is smaller than 10 to the minus 4. Okay? So, how much smaller? 10 to the 12. The difference between 16 and 4. It's like 1 with 12 zeros behind it, or in front of it. 6, 9, 12. When you read that number, you have 1,000, a million, a billion, and a trillion. So the range of our hearing is 1 trillion to 1. The softest sound power we can hear compared to the loudest sound power we can tolerate. The loudest sound power we can tolerate has 1 trillion times the power of the softest sound we can just barely hear. Okay? Now let's look at pressure. Forget power, leave it alone, look at pressure. Just talking about it, same thing. We're talking about the intensity of sound, but we're just talking about it in different units now, not in watts. Now we're looking at sound pressure in terms of dynes per centimeter squared. Remember, it's always per centimeter squared because it's force over an area. So, the softest we can hear, 0.0002 dynes per centimeter squared. And what is that? That's the softest pressure it took to hear a 1,000 hertz tone at 1 meter distance with 2 ears. In terms of pressure, this is 0.0002 dynes per centimeter squared against your eardrum. That's the pressure against your eardrum. If you were sitting 1 yard away from a speaker and a 1,000 hertz tone was being played from the speaker and they turned it down, 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 down till you couldn't hear it anymore, right at that point, you would be measuring about 0.0002 dynes per centimeter squared against your eardrum. Now look at this. The largest sound pressure you can tolerate is 200 dynes per centimeter squared. So what's the difference between the loudest and the softest in terms of pressure? Well, it's 1 million, not 1 trillion. Okay? 200 dynes per centimeter squared is 1 million times bigger than 0.0002 dynes per centimeter squared. So in terms of pressure, the range of our hearing is 1 million to 1. And if that mixes you up, go right over to this picture here that looks at the 2 thermometers. That's the way I'll always describe it. Okay? Boiling is boiling is boiling. Freezing is freezing is freezing. The loudest you can tolerate, call that boiling. The softest you can hear, call that freezing. Okay? So freezing right here, water freezes, the softest you can hear. Water boils, that's the loudest you can tolerate. Pressure you can think of in analogy as Celsius. Fahrenheit you can think of in analogy like power. Okay? The Fahrenheit thermometer just has more increments. It has smaller degrees. That's why it's 1 trillion to 1. That's why the range of the softest to the loudest is 1 trillion to 1. Celsius you can think of it by analogy like pressure. The range of our hearing hasn't changed. It's just that the degrees are thicker. Okay? And what's 1 million compared to 1 trillion? Well, power equals pressure squared. 1 million times 1 million is 1 trillion. But always remember, now all it means is that in terms of power, in watts per centimeter squared, there's just more increments. That's all. It doesn't mean that the range of your hearing has changed at all. Good. All right, we'll get out of that and look at our notes. This picture is positively frightening. I stay away from it. All right, so now we can move down to the next page so we can highlight what's important. I would kind of put a star by this too. There's 4 ways that you can assign numbers to things. You can name things with numbers, or you can order things with numbers in terms of rank. Tallest to shortest, lightest to heaviest, smartest to dumbest, whatever. Slowest to fastest. And then an interval scale is like inches on a ruler. You're not only ordering things in terms of numbers, but each item has equal intervals between. Okay, like 1 inch to 2 inch to 3 inch to 4 inch. Temperature, 5 degrees, 10 degrees, 15 degrees. Okay, but you can't really say that 10 degrees, or let's say, for example, say that 10 degrees is twice as warm as 5 degrees. Or that 50 degrees is twice as warm as 25 degrees. That's not really true. You know, 50 degrees is 25 degrees warmer than 25 degrees, and 10 degrees is 5 degrees warmer than 5 degrees, but you can't really say that 10 degrees is twice as warm as 5. So in order to be able to say something is twice as much as, or half as much as, or 3 times as much as, you need to define the ground. And that's what we do with the decibel. It's based on the ratio scale. Not only are things ordered and they're in fixed increments relating to each other, but we've also defined what 0 is. You've defined the ground. And what is the ground? 0 dB sound pressure level. And what is 0 dB sound pressure level? 0.0002 dynes per centimeter squared. And what is 0.0002 dynes per centimeter squared? It's the softest it took for a normal hearing human to just barely hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears. We call that the ground. 0 dB SPL. All right, good. Memorize that. That's just what I was talking about there, that relationship, okay? And if you're unsure, play it again in the Zoom session. Here we go. This is the third and final formula right here. Okay? If you have a different sound pressure level other than 0.0002 dynes per centimeter squared, you want to figure out what decibel that is. Okay? And the formula has 3 pieces. And the trick to remember in this formula is the bottom number is always 0.0002. That's the ground. What you're doing here is you're saying you had some other sound pressure. Okay? And you want to find out what dBSPL that is. You know that this one we've called it 0. 0 dBSPL. Now you have a different sound pressure, so you want to figure out what dB is that. Well, first of all, you take that pressure and you divide it by this one. You come up with a number, whatever number that is. What's the logarithm of that number? And in plain English, a logarithm is simply how many times does 10 have to be multiplied by 10 to equal that number? Now, if that sounds kind of strange to you, it is, because if you had some number over here and you wanted to find out what the logarithm is, and you'd have to, what about if you have the number 46? How many times does 10 have to be multiplied by 10 to equal 46? I don't know. It's going to be in a table in the back of some math book somewhere. Okay, I can't figure it out. I'm not a mathematician. So what we're always going to do here is just use rounded numbers, okay, to keep it simple, but to convey the concept anyway. All right, that's what we're going to do in the next slide. So here you go. Let's say you had a sound of, let's go to here. There you go. Let's say you had a sound of 0.002 dynes per cent. Whoops, 0.002 dynes per centimeter squared. Okay, so let's take that one. All right. You go over to your formula here and you say 0.002 divided by 0.0002. And if you did the math, you'd end up with the number 10. Now, how many times does 10 have to be multiplied by 10 to equal 10? 1. 10 times 1 is 10. Okay, so the logarithm of 10 is 1. And what's 20 times 1? 20. So go back to the picture here. 0.002 dynes per centimeter squared corresponds to 20. 0.02, if you divided that by 0.002, if you took this number, whoops, not that one, just the middle one right here, this guy, and you divided it by this, you'd end up with 100. See, there's 2 less zeros here, so you know 0.02 is 100 times more than 0.0002. So this divided by this is 100. What's the logarithm of 100? How many times does 10 have to be multiplied by 10 to equal 100? 2. 10 times 10 is 100. So what's 20 times 2? 40. and so on, and so on, and so on. Okay? 200 divided by 0.0002 is a million. How many times does 10 have to be multiplied by 10 to equal a million? Well, 10 times 10, I'll stop sharing here for a second. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000, times 10 is a million. So the logarithm of a million is 6. What's 20 times 6? 120. Share screen. Have a look. All right, that's the relationship. Now let's take this unit home and look at a few things. Right over here. Right here. Memorize this. It's on the midterm. Due to logarithms, because of all that stuff we've talked about, just because you double the sound pressure, that doesn't mean you double the decibels. Remember, it's all based on logarithms. So, if you double the sound pressure level represented by 20, you don't get 40. You actually get 26. And only if the sounds are identical. So, for example, you have a 1,000 hertz tone of 20 dB SPL. And you have another 1,000 hertz tone of 20 dB SPL. Put them together, you got 26. Okay? So every time you have a machine making 90 dB SPL, and you put right beside it another machine making 90 dB SPL. If the two machines were identical, you'd have a sum total of 96. Okay? So when you double the sound pressure, you go up by 6, and that's only if you are adding together two identical sounds. In real life, that normally doesn't happen. Okay? Two machines, even if they're made by the same company, same make, same model, they're going to be slightly different. They're going to be. So, if that's the case, let's say you have machine A making 90 dB SPL and another machine B making 90 dB SPL. The sum total now is not 96, it's 93. Okay? If I'm talking at 60 dB SPL and another guy comes and stands beside me and he's talking at 60 dB SPL, well, that guy's voice is different from my voice. So the sum total is going to be 63 because we're different. All right? If we were identical, if one Ted is talking at 60 dB SPL and then a clone of myself is talking at 60 dB SPL, well, then the sum total would be 66. But as far as I know, that's never really happened in life. Okay? It just doesn't go that way. All right. So very important. Think of a choir. One lady is singing at 70 dB SPL. 10 ladies singing at 70 dB SPL. What's the sum total? Well, when you increase the pressure by a factor of 10, how much do you go up? Let's go back to our picture again. When you increase the pressure by a factor of 10, how much do you go up by? When you increase the pressure by a factor, see all these numbers on the bottom? They're always dealing with tens. This one's 10 times as much as this. This one's 10 times as much as that. This one's 10 times as much as this. So every time you are increasing the pressure by a factor of 10, you're going to go up 20 dB. So if you had one lady singing at 70 dB SPL in a choir, and then 10 identical ladies singing at 70 dB, your sum total would be 90, because 70 plus 20 is 90. I've increased the pressure by tenfold because one lady was singing at 70 and now suddenly there's 10 identical ladies singing at 70. But that never happens in life, okay? So the real point is you have one lady singing at 70 dB SPL and now you have 9 other ladies are added. So now you have a sum total of 10 different ladies singing at 70 dB SPL. You don't go up by 20 now. Now you go up by 10, half of it. Just like doubling the sound pressure of two different things. You go up by 3, okay, and 3 is half of 6. 6 is what would happen if the two things were identical. 6 is half of 3, 10 is half of 20. Anyway, this is the kind of knowledge you should know as to why a choir won't make you deaf. Okay? Because what does noise-induced hearing loss start at? 85 dB SPL. Noise-induced hearing loss, intensity and the decibel. So this little section here is this little section here is very important, and it's talking about all that stuff, whether they're identical or whether they are not identical. In real life, you're normally not adding things together of equal frequency and phase. They will be different. So 45 plus 45 in this case is 48. All right, that's what that whole section is talking about. Put a star by that and make sure you read it carefully. And then in this section, put a star by this too, because in real life, you're often not adding equal things together. Okay? You might be saying you've got 50 dB SPL, and now you're adding 40 dB SPL. So maybe the frequencies are all different, but now you're adding two different intensities as well. They're not just different in frequency, but now you're adding sounds that are also different in intensity. So what's 50 plus 40? In this case, it's basically 50. An elephant plus a mouse is an elephant. Okay? So when the difference between the two levels begins to be less than 10 dB, then you'll start adding little bits. And if there's no difference, oh, look at that, now you're adding 3 again. Okay? So that's what this pick, but why am I saying 3? Because you're assuming in normal life that the two sounds are always different in frequency. They're almost never identical in frequency. Okay? So that's why you're just saying 3 instead of 6. So when you're adding two sounds together and they are equal in intensity, there's no difference between the two levels, you're going to go up by 3. And that's what this picture here was showing you. Okay? If there's no difference, you're going to go up by 3. To add, for example, 85 to 90, these are only 5 dB difference. So you're going to look on this curve, what's the difference? It's 5. And then you're going to go to the left, and that's what you're going to add to the highest of the 2 dB levels. This isn't on your midterm, by the way. But questions like 60 dB SPL plus 50 dB SPL, that will be on the exam. Like, what's the sum total? You should say the answer is closest to 60. It'll probably be 60 point ... But basically, an elephant plus a mouse is basically an elephant. And that's all because of logarithms. It's all because of logarithms. Blame the logarithms. All right. Scroll down. Take you to the end of this unit here. Okay. We should have a grip on typical sound levels. Okay. Make sure you have these typical sound levels. And what causes noise-induced hearing loss? 85 to 90 dB SPL for up to 8 hours a day. Okay, that's the anchor. Put a star by that one. Make sure you know that. Okay, that's what can cause permanent noise-induced hearing loss. And because of logarithms, if, for example, the state law said 90 dB SPL for 8 hours a day, if you increase the pressure or the sound to 95, then your allowed time exposure gets cut in half. So the rule is every time you go up by 5, your allowed time exposure goes down by 2, or goes down by half. Earplugs attenuate. That word is an important one. Okay? Attenuate means to quiet. Okay, and to prevent noise-induced loss, what's the attenuation of your earplugs? Basically, you know those yellow EAR plugs, the yellow sponge plugs that people roll up and stick in the ear? Those attenuate by about 30 decibels. They attenuate by about 30. The bigger muffs like this will probably attenuate by a little more. Cotton balls in the ear hardly attenuate at all. They don't do very much at all. Okay. Don't worry about the dBA so much. We're just about at the bottom here. Oh, yes, and let's see if we just got a little bit of stuff here. I want to make sure. Oh, yeah, absolute versus relative values. Make sure you have a handle on that. Because there are some times when you can add dBs together, like 1 plus 2 is 3. Think about the machines again. 2 different machines. And I'll stop sharing for a second. 2 different machines. 90 dB SPL, 90 dB SPL, put side by side, 93. What was the increase? 3. That was the gain. And in hearing aids, gain. Input is the sound coming into the mic of a hearing aid. Gain is what's being added, and output from the hearing aid is hitting your drum. Input sound and output sound from a hearing aid are always measured in dB SPL. They are, whenever you see the word SPL, that always means that the pressure of sound is referenced to 0. Okay, it's referenced to the ground, always. Okay, whenever you see simple dB, it means gain, and it's a relative decibel value. And think about it in like time. If you're in Missouri, you're on Central Standard Time. That's your reference. So is it 4 p.m.? Is it 6 p.m.? 5 p.m.? Well, those are absolute time values. They are referenced to Central Standard Time. I'm not in your time zone. I'm in Pacific Time. So right now it's 20 minutes after 10. In Missouri, it's 20 minutes after noon. Okay? So my reference is different. I'm here in Pacific Standard Time. Well, whatever. But if you think of the sound, or think of the term 2 hours, 2 hours, that's a relative time value. I can add 2 hours to 4 p.m. and now I'm 6 p.m. I can add 2 hours to 6 p.m. Now I'm at 8 p.m. So when you think of a term called 2 hours, that's a relative time value. When you think of 4 p.m., that's an absolute time value. And in decibels, it's the same thing. You can't simply add 2 dB SPLs together. 90 and 90 equals about 93. Okay? You can't add them together like 90 and 90 is 180. But the only time you can do that is when you're adding an absolute value, which is called some X dB SPL, plus a relative decibel value called simply dB. Okay, so in that case, 90 plus 90 dB SPL plus 3 dB equals 93 dB SPL. See what I just did? Okay, because 93 is 3 more than 90, so that was a gain or an increase of 3. And that increase is called a relative decibel value. Excuse me. In hearing aids, always remember, input plus gain is output. You will be learning this a lot more in upcoming semesters, believe me, okay? But you're just touching the ground with it here. Input is dB SPL from the room, from the whatever, from traffic noise, whatever, coming into the mic of a hearing aid. And the hearing aid is adding gain. Here, let me just pick out a hearing aid, just for fun. Here's a big old hearing aid, an ugly old hearing aid. And the microphone of the hearing aid is going to be right at the top. There's a little dot there. You might see this little dot. That's the mic of a hearing aid. It's picking up the sound from the air. That's the input. And that's some dB SPL. What is the hearing aid adding to it? Gain. Okay, the hearing aid is increasing. And that gain is always dB. And then what's coming out from the hearing aid into your ear canal, that's called the output. And that's dB SPL again. So dB SPL plus dB equals another dB SPL. And when you're doing that, you can, C-A-N, can add like 1 plus 2 is 3. 50 dB SPL input plus a gain of 50 dB equals 100 dB SPL output. Thank goodness. See, we don't have to deal with logarithms, but you have to get through hell in order to get through to heaven. And you had to understand all about the decibel in order to, now that you've eaten your potatoes, now you can have your dessert. And thank goodness we get the dessert, the cake. Okay, that's our field because we deal with hearing aids. And when we're dealing with hearing aids, we're always adding absolute and relative dB values together, always. And when you're doing that, you can add like 1 plus 2 is 3. And you don't have to think about the logarithms. Why? Because you're at, look, I can add 50 dB of gain to a 10 dB SPL input. I can add 50 dB of gain to a 20 dB SPL input. I can add 50 dB of gain to a 30 dB SPL input. See what I mean? The gain is relative. dB-SPL means the value was absolute. In English, that means it's referenced to the ground. Simple dB is a relative intensity value. You can add that to any absolute value. All right, I think we've beaten that horse to death. Okay, and the last unit was the most recent, and so we don't need to worry so much about that particular unit, but pulling it up, complex sounds, if we quickly highlight here the important things to remember about that. Here you get into a spectrum. Make sure you know what the difference is between a sound wave and a sound spectrum. And the advantages of a spectrum is that you can see what the individual frequencies are. You need to know what fundamental frequency is, and you need to know what the differences are between harmonics and octaves. Harmonics are equal multiples of the fundamental. Octaves are when you double the frequency. You don't need to know anything about square waves, triangular waves, sawtooth waves. We don't care. That was just shown for fun, just for the sheer heck of it. Beats, you should know. If you're adding two tones that are very...
I have a question.
Oh yeah, hey, good.
When is our midterm?
I believe it opens up tomorrow.
Okay.
It's not proctored, but it opens up tomorrow. That's
Okay.
what Lynn Royer has said. And I think it's available for a week.
Okay, cool.
Cool, good. Glad you asked. Yes, finally it feels better not to just sit here talking into a machine. I'm actually talking to a person. Great. All right. And beats are when you're adding two frequencies that are close together. A 1,000 hertz tone plus a 1,001 hertz tone together, you're going to hear wow, wow, wow. Right? What you're going to hear is the difference between the two frequencies. When they get far, far apart in frequency, you begin to detect two separate tones. Moving on down here, see if I can. This thing will let me. Okay, here we go. Spectrum for three complex sounds. Well, that can be kind of useful to show here. I've always liked showing that particular picture. But here's a spectrum. Just there you go. Just showing you individual discrete frequencies that decrease in amplitude. They don't have to. They can go straight across. They can. Here's a spectrum that's going straight across, and it includes everything underneath here. This is a spectrum that includes everything underneath here. It's got more amplitude in the high frequencies than in the low frequencies in this case. Here's a sound wave and its spectrum, a sound wave and its spectrum, a sound wave and its spectrum, and so on. Adding the sound waves together, you get this complicated wave. Adding all frequencies together on a spectrum, you get this. Okay? Spectrums are very good at telling you what the individual frequencies are. If I looked at this wave here, I wouldn't be able to tell you. Here you can. So an analysis of sound waves that breaks it down into the spectrums is called a Fourier analysis. Okay, not that one. I don't want this one here. Spectrum of, where am I here? Fourier analysis. That's when the sound waves comes into the machine, and the machine or the analysis thing breaks it down into the individual frequency components, and it will show you a spectrum. Very good. Enough on that. All right. And this spectrum here of three complex sounds together. I don't want that one. There. I like this picture, because it's showing you three complex sounds, and they may have all the same fundamental frequency and identical harmonics, equal multiples of the fundamental, but look at the different amplitudes. So these three different instruments are going to sound different in quality. because they resonate at different frequencies. Their mass and stiffness are different. And so they're going to offer different opposition. Okay, this instrument's going to offer exactly the same resistance, friction, to all these frequencies, but it has very different opposition to different frequencies than this instrument does, than this one does. So that's the issue here. This one may be offering identical resistance to all these frequencies, but because of its mass and stiffness, it's going to resonate with various frequencies that are very different from this one. And same with the bottom one. Resonance is when your opposition to mass is identical to your opposition due to stiffness. That's probably as deep as we ever want to go in that topic. Moving on down here. Yeah. So you can think of resonance or impedances kind of like filters. Here. This top musical instrument. It's filtering out this one. It's letting this guy get through. This instrument here is filtering out this one here, and it's sort of letting these get through a bit. The bottom one is filtering out 300. It doesn't like it. Filters out 1800. It resonates with these. So when you hear the term filter, think about a vacuum cleaner with a filter in it. It's letting the air pass through, but it's collecting the dust. Okay? In sound waves and things that transmit sounds, things that transmit sounds also act as filters. They impede certain sounds and they resonate with other sounds. So you can think about that conceptually as filtering. Okay. And when you're in complex sounds, realize that there are various different kinds, that there are tonal and non-tonal. Where do we begin? Right at the very top of the notes here. Periodic or non-periodic. Put a star by that. Okay? Periodic means they repeat over time and they will sound tonal. If the sound wave does not repeat over time, if it looks like a scratchy, raggedy mess, here, look at the sound wave. No rhythm to it whatsoever. It's just that's noise. Okay? And if the noise has a flat spectrum, it's called white noise, because the color white includes all colors. If the spectrum goes down like this, it's called pink noise, because red and pink in terms of colors is the lowest frequency. So pink noise means that it's got more energy in the lows than it does in the highs. And a spectrum of speech is a lot like pink noise. And last of all, in our notes, we covered transient noise versus turbulent noise. Right here. Underline that. Okay? And then we bring it to speech. Oh, do know what broadband and narrowband noise is. You got broadband noise, white noise, pink noise. Those are all broadband. Narrowband noise just means that the width of the noise is very narrow. Okay? So the width is here, or maybe the width is here, or maybe it's here, or maybe it's at this frequency, or maybe it's at this frequency. Okay? Narrow bands of noise versus wide bands of noise. All right. Share screen and get done. In speech, make sure we have a handle on consonants. Here we go. This is something also very useful to know. All right. And there's that vocal tract thing and helium speech again. So now we are kind of almost to where we started. But do know that vowels are tonal, they're periodic, and they're low frequency, and I would right underneath low, I would also say loud. Unvoiced consonants, non-periodic, therefore they are noise, they are high frequency, and I would write underneath here, soft. And that's why the spectrum of speech is like this. So vowels would be here, unvoiced consonants would be here, and voiced consonants would be here. And in our notes, we finished with this. An F is an unvoiced consonant. And if I add a voice to it, I get a V. S, S, add a voice to it, I get a Z. Z, S, Z. P, 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 add a voice to it, B. Paul or Bob. B, B, P, P, D, D, T, T. Notice that your tongue is doing the same thing when you're saying the letter D versus the letter T. D, D, T, T. Okay? K, 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 G, G, G. Back of your tongue. Ch, ch, j, j. Say the word judge. J. Think of where your tongue is. Judge, or say the word church. Same place. Okay? Voiced consonants just happen to fit sort of between vowels and voiced, unvoiced. In other words, they're part tonal and part noise. So in our lovely little spectrum over here, voiced consonants would be in the middle. Okay, I be done. What I'm going to do here is stop sharing and stop recording and wish you good luck and success on the midterm. Glad we could do this review for you, and here's hoping you all do well. All right, I will stop recording now.